Welcome to Math 2320, Section 6.1, where we begin to look at series solutions. This first section, 6.1, is basically a review of the things that we saw in Calculus 2 on series. So supposing we have a series here. Index going from 1 to infinity, we'd like to know if it converges or diverges. One of the ways to do that is to do the ratio test. And the ratio test forms the absolute value of the a n plus 1 term over the a n term. So you form this ratio, take the absolute value and look at the limit. Now, if the limit is less than 1, you get absolute convergence, which implies normal convergence if the absolute values were not there. If L is running off to infinity or any number bigger than 1, the series diverges. And if the limit is exactly 1, the test provides no information, which means you need to try something else. Alright, so that's just a basic test we're going to be using often here with series. Alright, so looking at question 1. Question 1, we have n equals 1 to infinity minus 1 to the n over n x to the n. So this is my function of x, so f of x equals this power series. So the question is, well, what x's can we use? Well, if you look at this, you're guaranteed it's going to work for x equals 0, because if x is 0, all the terms are 0. So certainly an infinite sum works. So let's see, what does this mean for our ratio test? So what I do is I take a n plus 1, so I substitute in n plus 1 for all of the terms, put that over a n. And so now when I simplify this, I'm going to put things that look alike together. So I've got the minus 1 terms, the n terms, and the x terms. Well, let's see. The minus 1 terms really go away because of the absolute value. So I'm left with n over n plus 1, and x to the n plus 1 over x to the n is simply x. I don't need absolute values on the n's because n is going to positive infinity. Well, what happens? Well, as n goes to infinity, this ratio goes to 1, and so I get 1 times the absolute value of x. So, as long as the absolute value of x is less than 1, or without absolute values, x is between minus 1 and 1, we will get absolute convergence. So you see, here's 0 that I already knew worked, and now I can go as far as minus 1 and 1. So the radius here, radius of convergence, is 1. Now, with this technique, it will give me the radius of convergence and where. But often, I need to check each endpoint to see if it works or not. So, what if x is 1, the right endpoint? So if I plug in 1 to the n, well, 1 to the n is just 1, so I get nothing. And so I've got this series. This is an alternating series because of the minus 1 to the n. And by the alternating series test, then this series does converge. And so the right endpoint does work. Alternating series test basically says, is the series alternating, and does the limit of the terms go to 0? All right, and is it decreasing? All right, so what about the other endpoint? Well, minus 1 plug in. So that's minus 1 to the n times minus 1 to the n, which is minus 1 to the 2n. Well, 2n is always even, and so minus 1 to an even number is a positive one. Well, this is a divergent p-series where p is 1, which is the harmonic series, and we know that this diverges. So no, I do not get the other endpoint, just minus 1 to 1 with the right endpoint included. All right, what about question 2 here? We'd like to know what x's we can make this work. Well, let's see, 1x I already can guarantee you works is 4. How do I know so quickly that 4 works? Because 4 minus 4 is 0, and so I'm guaranteed at least 1 point. Question is there more? Well, let's find out. So form the ratio test. Put in n plus 1 in place of all the n's. Put a n on the bottom. Put things that look alike together. Minus 1's will go away. 8 to the n over 8 to the n plus 1 gives me a 1/8. X minus 4 to the n plus 1 over x minus 4 to the n just gives me absolute value x minus 4. When I take the limit, n is not anywhere in there, and so this is my limit. I want it less than 1 or the difference less than 8. So, removing the absolute value that says it's between minus 8 and 8, add 4 to both sides, and I get now minus 4 to 12. So here's the original 4. The radius of convergence I see is 8. We check the two endpoints to see if those work or not. So let's see, plugging in minus 4. Minus 4 minus 4 is a minus 8 to the k. So I split this off as minus 1 to the k, 8 to the k. Alright, well, the 8 to the k parts cancel. I get minus 1 to the 2k, which is just positive 1. So I'm adding up 1 plus 1 plus 1 plus 1, which clearly diverges. If I plug in 12, I get 12 minus 4 is 8. The 8k's cancel. And now I get this alternating business. Minus 1 plus 1 minus 1 plus 1, which again diverges. And so I only get my original interval of convergence and not the endpoints. Question 3. All right, let's see what happens here. We look at the ratio test. I plug in n plus 1 every place where there was an n. The only place to be careful here is in this point. It's 2 times that. All right, everything else is fairly recipe-ish. So let's see, when we simplify and put everything together. Oh, I forgot to mention, what was our point we were guaranteed works? Well, let's see. We are at least guaranteed that 0 works. More on each side, that's the thing in question. Alright, so back to where we were at. Putting like things together, I get 1/16. I've got an x to the 2n plus 3 over x to the 2n plus 1. So top exponent minus the bottom exponent. And so what do I see? I get 1/16 absolute value, x squared. Because of the squared, I don't need the absolute value. Take the limit. There are no n's in it. And so I want this to be less than 1, which says x squared less than 16, or x to be between -4 and 4. So here was our original x we were guaranteed. We do get more, and the radius of convergence is 4. What about the two endpoints? Let's see. Plugging in -4. Let's see, that's -4 to the 2n plus 1. So I split off the -1 part, and now I'm looking at 4 to the 2n plus 1. I split that into 4 to the 2n times 4 to the 1. Well, let's see. 4 to the 2n is 4 squared to the n, so those cancel. The -1's I've got here, and here's a 4. So I'm adding up things with lots of 4's in it. Clearly that is divergent. Plugging in +4, things are not any better. This is 4 to the 2n. I get this 16 to the n again. I get a leftover 4, which doesn't go away. And so now I've got -4 plus 4 minus 4, so on. And so the only part that works is -4 to 4 with a radius of convergence of 4. All right, what about a Taylor series for the cosine centered at 2 pi? Well, if you remember Taylor series, also in Calculus 2, the Taylor series centered at x equals a looks like the following. Here's the a where we're centered on. The coefficients are the first, second, third, fourth, nth derivative at the place that you're centered on over n factorial. So let's see, C0 is f at a, which is cosine of 2 pi, which is 1. I look at the first derivative. First derivative of cosine is minus sine. But anytime I'm going to get a sine term, the sine of 2 pi is 0. That's why they say use the periodicity of the process to kind of know what's going on. So for this C2 term, that's the second derivative, I'm back to a cosine, and so I get -1. C3, I'm back to a sine. Sine is 0. C4, back to a cosine, which now, because I've alternated with plus minus plus, I'm back to a positive cosine, which is a 1. If you look at the denominators for C2, 2 factorial, C4, 4 factorial. All right, well, let's see. If I consider C0, k to be 0, C2, k to be 1, C4, k is 2, I get the relationship for the ck terms. And so our power series representation then looks like the following, and this is centered on the particular a that they asked us it to be centered on. And finally, in question 5, we are given a first order differential equation here, and so we're trying to find a power series solution. All right, so this is what it's going to look like. If I spread out the terms, it looks like this. What's y prime? Well, the derivative of a constant goes away. This 1 comes in the front. Derivative of a constant times x is c1. And so similarly, all of these follow by the power rule. And so y prime is this particular term. Plugging it in, we know that this thing is supposed to equal to 0. So that's to our advantage if this is to be equal to 0. The only tricky part is the index on these two is different. So essentially, I'm shifting the index. So I shift the index. So if it used to be 1, and now I want to start it at 0, this is n plus 1. I'm shifting this by 1. So xn, this n, cn plus 1. Now that I've got the same sum, same index, I can put them together. And so what I see is I've got this set of terms in front of the xn part. So if this sum is to be 0, then this piece must be 0. And so I get a relationship between cn plus 1 and cn. So c1, meaning n is 0, I get c1 is 7c0. And so I keep stepping through this. What's c2? What's c3? But it's recursive in that it's defined in terms of the one previous to it. And so if you trace this out, you get the relationship between the nth term is just a power of 7 to the n factorial c0. So since they all have c0 in it, factor it out. And so here is our power series solution to the first order problem that they gave us. So if you're unfamiliar with power series, dig out your calculus book and look a little bit at power series, Taylor series, and rules for convergence and divergence.